You know, there are these invisible forces all around us shaping our world. Today, we're going to dive into the secret life of electric charges and see the fascinating dance they do when they take a spin in an electric field.
So when you look at a diagram like this, you're not just seeing a bunch of squiggles. No way. These are actually maps that chart the direction and strength of invisible electric forces. And believe it or not, each one of these patterns is telling a story.
And to understand these stories, you got to know the language, right? You got to meet the main characters. Well, our main character today, the most basic pattern you'll find is the electric dipole.
So what exactly is an electric dipole? It's actually super simple. Just picture a pair of charges. One's positive, one's negative. They have the exact same strength, but they're opposites. And they're separated by a teensy tiny distance.
And this is what it looks like out in the wild. This is our main character, the classic dipole. See how those field lines just burst out from the positive charge and then loop right back around to land on the negative one? That pattern is its story. It's how it communicates its force to the rest of the universe.
And listen, this isn't just some abstract thing we talk about in physics class. This simple little pair of charges, it's an absolutely fundamental building block. If you want to understand how a water molecule works, or even how the materials inside your phone interact with electricity, you have to understand the dipole.
Okay, so we know what a dipole is when it's just hanging out by itself. But things get really interesting when it's not alone. So what happens when it meets an external electric field?
All right, let's set up the experiment in our heads. We take our little dipole and we just drop it into a perfectly uniform electric field. What do you think is going to happen? Is it going to get shoved across the room, maybe pulled apart?
Well, here's what's really going on. That external field, which you can see as those straight lines, it starts pulling on each charge. It grabs the positive charge and yanks it one way, and it grabs the negative charge and yanks it in the exact opposite direction.
Now, because those two forces are perfectly balanced, equal strength, opposite directions, they completely cancel each other out. So the net force on the whole thing is zero. The dipole isn't going anywhere. It's not getting pushed or pulled from its spot.
But, and this is a big but, just because there's no net push doesn't mean nothing's happening. Think about it. You've got a force pulling one end this way and another force pulling the other end that way. The result isn't a push, it's a twist. In physics, we call that a torque.
And we actually have a way to measure this twisting tendency. It's called the dipole moment. You can think of it as a little arrow, we call it P, that points from the negative charge to the positive one. It's like the dipole's own internal compass needle. The stronger that dipole moment, the more powerful the twist it's going to feel.
And the whole point of this torque is to rotate the dipole. It's going to keep twisting and turning it until it lines up perfectly parallel with that external field. It's almost exactly like a compass needle snapping into place with the Earth's magnetic field. Same principle.
Okay, so that all makes sense for something that's already a dipole, what we call a permanent dipole. But what about things that aren't dipoles to begin with? This is where our story takes a little plot twist.
Yeah, what about something like a perfectly symmetrical atom? You know, it's got a positive nucleus right in the middle and a nice, even cloud of negative electrons all around it. The charges are perfectly centered, there's no built-in dipole there. So what happens when that gets put in an electric field? Well, watch this. When you put that neutral atom into an external field, something really cool happens. The field pulls on the positive nucleus and the negative electrons in opposite directions, stretching the atom out just a tiny bit. And that little separation of charge, it creates a temporary dipole. We call this an induced dipole. So let's just break it down. We've got two types now. On one hand, you have the permanent dipole, like a water molecule, which is just naturally lopsided. It's born that way. And on the other hand, you've got an induced dipole, which is created on the spot only when you expose a neutral atom to an external field.
But here's the beautiful, unifying part. It really doesn't matter if the dipole was permanent or induced. The final result is exactly the same. In the end, the dipole is going to twist and align itself parallel to that external electric field. That's the end game for both of them.
At this point, you might be thinking, okay, cool, spinning molecules, I get it. But so what? Why does any of this microscopic spinning and aligning actually matter in the real world? Well, let's zoom out and look at the bigger picture.
This is the really crucial part. Once that dipole is all lined up, it generates its own little electric field. And if you look closely at the field lines inside the dipole, you'll see they point in the exact opposite direction of the big external field that lined it up in the first place.
So what does that mean? It means the dipole's own internal field is fighting back against the external one, and the result is that the total electric field, right there between the charges, gets weaker. It's reduced. The dipole actually works to weaken the very field that aligned it. How cool is that?
All right, let's do a quick recap. What have we learned? 1. Dipoles are just a pair of equal and opposite charges. 2. In an external field, they don't get pushed, they feel a torque, a twist. 3. That twist makes them rotate and line up with the field. And 4, the big one, this alignment creates an opposing field that weakens the total electric field in its vicinity.
And that leads us to one final huge idea. We've just seen what one tiny little dipole can do. It can slightly weaken an electric field. So the question is, what happens when you have trillions and trillions of these dipoles all packed together inside a material, all aligning at the same time? Because that collective effect, well, that's where things get really powerful. That's how we build things like capacitors. What do you think happens then?